we want to look at the function f of xy equals x plus square root of y. And we're going to look at this at primary point 4,9, then at the point 4.19 and 4,9.2. Now ultimately what we're trying to do is figure out how the graph behaves, the graph of this function of two variables behaves near the point 4, 9. Okay, near the xy coordinates 4, 9. Now, I've sketched just a schematic x, y, z, x this way, y this way, z this way, a set of coordinate axes here, and I've sketched a point here that I'm going to call 4, 9, 0. Now that of course corresponds to x equals 4, y equals 9, z equals 0. In other words, z equals 0 indicates that we're in a plane, well actually in the xy plane. Then we have the point 4.190, which has the same y coordinate as this one, and it's still in the xy plane because of the 0. But of course the x values change from 4 to 4.1. Now what this means is, now I've drawn an auxiliary x-axis here, an auxiliary y-axis here. These are not the x and y axes. It's like an x and a y axis if the origin was at 490, and it's just there to help us maintain our orientation and see what our directions are. So from 490 to 4.190, x changes by 0.1, which means we have to use move 0.1 unit parallel to our actual x-axis. In other words, from this point along our auxiliary x-axis, our x-prime axis. So we move 0.1 unit here. So now we have this segment that has length 0.1. And similarly we move 0.2 units from 490 to 49.20 in the y direction. So we have 0.2 units here. Now the value of our f of xy function when x is 4 and y is 9 is easily calculated to be 7. So we're going to sketch a segment in the z direction here that's 7 units long. Now of course if this is 0.1 and this is 0.2, these two are more or less to scale, but of course 7 on the scale of these segments would be much longer, so we're just doing really a schematic. This side here, this segment here would actually be several feet long. Okay, now from there I'm going to draw the rest of a rectangle, a 7 by 0.2 rectangle, with making right angles with the coordinate axes and so forth. So we have 7 here, we have 0.2 up here. In this direction, I'm going to do the same thing. I'm going to first sketch our rectangle. Okay, it's 7 by 0.1. So now we can see this is kind of like two walls meeting at a right angle. Now let's consider the value of the function when x is 4.1 and y is 9. It's not going to be 7. Actually, if we calculate it, it's going to be 7.1. This means that we have to go 1/10 of a unit higher. Now of course I'm exaggerating the scale here, but let's say that's 1/10 of a unit. And now we have an approximately straight line between here and here. Why is it approximately straight? Because the second derivatives of this function are not that big at this point. There's not going to be much curvature to the actual graph between here and here. But the graph of the f of xy function, which will be some surface in 3 dimensions, is going to be intersected by this plane, the plane of this rectangle, the plane parallel to the x-axis. In other words, a plane, it's actually the plane x equals 4. That intersection with the actual curve is going to be very close to a straight line. As a matter of fact, since it's linear in x, it is actually going to be a straight line in this plane. Now, this auxiliary y prime axis, x is constant, x is always equal to 4, on this line, just as y is always equal to 9 on the x prime line. So this rectangle is in a vertical plane parallel to the y-axis. The value of the function, if we evaluate this function at 9.20, the value turns out to be about 7.03, so that this little segment here has length 0.03. This little segment here has length 0.1, and the value of the function is now here, and we sketch a straight line. Now, the y dependence of this function, and I think I said maybe this y prime axis is constant, y is a constant x is constant 4. Okay, x is constant, but y is changing, and it's changing according to a square root. Square root is not linear, so that there's actually some curvature. But over a change in the y value of 0.2, the curvature is not going to be very significant, and if we don't look very, very closely, we're not even going to see the curvature. We might not even see it if we look really closely. It's there, but it might be microscopic in some sense. Okay, so now we have a picture of a segment in a plane parallel to the xz plane of a segment that pretty much runs along the graph, and a picture in a plane parallel to the yz plane of a segment, again, that pretty much runs along the graph. This one actually does run along the graph because x is linear. This one doesn't exactly run along the graph because square root of y isn't linear, but it's very close. And in any case, this segment here is tangent to the curve, to the surface f of xy at this point, and this line segment here is tangent to the surface at the same point. Okay, so we have two tangents to the surface here. The coordinates of this point are, of course, 4, 9, 7. And we have two tangents. If we can get vectors along these two tangents, or parallel to these two tangents, then we're going to have two vectors that are tangent to the plane and a point on the plane, so we can find the surface that contains this line, and that surface will be very close to a tangent plane at this point. And we're going to do that in the next video.